Assalamu alaikum, my dear student. Today we are going to discuss the chemistry of alkyl halides. And in today's lecture, we will discuss what are alkyl halides and how to name alkyl halides and types of alkyl halide. We have different types. And then we will discuss the physical properties and followed by the reactions of alkyl halide. In reaction of alkyl halide, we will mainly cover nucleophilic substitution reaction in today's lecture, while elimination reactions of alkyl halide will be discussed in next lecture. So let us start the alkyl halide. What is alkyl halide? When alkyl is directly bonded with halogen are known as alkyl halide. And generally, the alkyl should be sp3 hybridized. So we have the tetrahedral carbon atom in this case. And we know that carbon have 2.5 electronegativity, while in halogen, fluorine is the most electronegative element, and it is not considered as a good, the leaving group. So we will not discuss the alkyl halide when we have the fluorine as the halogen. Now let us see the other alkyl halide when carbon bonded with the chlorine or carbon bonded with the bromine. In case of alkyl halide, the bonds are little bit polarized because of the electronegativity difference. And while we have the iodine, in iodine case, it is have the same or the equal electronegativity because carbon and iodine have 2.5 electronegativity. In this case, we do not have basically the permanent dipole, but the bond is easily polarizable. It is because of the size of the iodine, because iodine is very much bigger in size. And iodine is a good leaving group due to its polarizability, that is, its ability to stabilize the charge, as I discussed already, due to its large size, large atomic size. Uh, Now we will discuss that how we can name alkyl halide. Now student keep remember all rules naming alkyl halide are same as we have discussed in case of alkanes. If you know how to name alkane, if you know how to name alkene, you can easily name any alkyl halide. Okay. Now I am not focusing all rules, but I will focus only the rules for halogen containing alkane. Now, the first rule is halogens are treated as substituents, as a prefix. It means halogens cannot be the parent chain. It will always be read as halo, means chloro, bromo, iodo, when it is directly bonded with any alkyl chain. For example, fluoro, bromo, chloro, or iodo. Similar rules are alkyl as alkyl substituents. For example, in this case, I gave a 4 carbon chain alkyl. At carbon number 1, chlorine is attached, and at carbon number 2, bromine is attached. Now, these halo group or the chloro or bromo group will be prefixes as chloro or bromo. We have to take care the alphabetical order. According to the alphabets, bromine will come first and then chlorine. So at carbon number 2, bromo is there, and at carbon number 1, chloro is there. So we will read as 2 bromo, 1 chloro, butane. In the next example, I gave a 2 chlorine group at carbon number 1 and carbon number 4, and we have a methyl group at carbon number 3. But according to the alphabetical order, chlorine will come first. So, but there are 2 chlorine at carbon number 1 and 4, so we will read as 1, comma 4 dichloro, and at carbon number 3 we have a methyl, so we will write 3 methyl, and total 6 carbon long chain we say the 1 for dichloro 3 methyl hexane. Now our next topic is types of alkyl halide. It is very important. You know that we have different type of carbon. We have discussed already in our previous lecture, like 1 degree carbon, 2 degree carbon, and 3-degree carbon. So that's why we may have the different type of the alkyl halide as well, and we have different type of the type of hydrocarbon like saturated and unsaturated. So all these type of hydrocarbon when bonded with the halogen will have the different type of alkyl halide. Let us see. As you know, this is the general structure of any alkyl halide. Now, in this case, this carbon is sp3 hybridized, and the structure geometry is tetrahedral. Now, I'm writing here halogen. Halogen means chlorine, bromine, or iodine. Fluorine is not the good leaving group, so that's why I'm not writing here. Now, as you know that this carbon and halogen bond is polarized. Polarized means due to electronegativity difference, and it has the positive and negative center. Now this is basically the nucleophilic center, and this is basically the electrophilic center of this alkyl halide. Now generally, as I discussed, a carbon halogen bond is polar with partial positive charge on the carbon and a partial negative charge on the halogen. Now, these are different type of alkyl halides. Now, as I discussed that we may have the 1 degree, 2 degree or 3 degree alkyl halide depending that how halogens attach with the carbon. Now, in this case, you can see this halogen is bonded with a carbon who bonded with only one carbon. So, in this case, this is known as the 1 degree alkyl halide. And in the second example, this bromine is directly attached with the carbon. This carbon is directly attached with two more carbons. So this is the example of 2-degree carbon atom or the secondary alkyl halide. In the third example, this iodine is directly attached with the carbon, and this carbon is bonded with three more carbon. So this is the basically an example of 3-degree alkyl halide, or this carbon is known as the 3-degree carbon atom, yeah, three carbon atoms. Now, it is not necessary that halogens only attached with the saturated alkyl group. We may have the halogens attached with the unsaturated alkyl group. It could be olefins, it could be alkyne, it could be the benzene ring as well. So how we can distinguish, or we can have the structure of these type of the alkyl halide. Let us see. For example, if we have the unsaturated alkene, and in case of unsaturated alkenes, halogens directly attach with the carbon-carbon double bond. This is known as the vinylic position. Okay, and this type of alkyl halide is also known as alkenyl halides because this carbon atom is sp2 hybridized. When halogens directly attached with the aromatic ring, this is known as the aryl halide or the aromatic halide. When halogens attached with sp carbon or in the triple bond, it is also known as the acetylenic halide or the alkynyl halides. Now let us see some physical properties of alkyl halide. These are basically a low soluble, or they have the low solubility in water because of the structure. Small chain alkyl halides are soluble in water, but as the chain increases, its solubility decreases. They are miscible with each other and relatively non-polar solvent, definitely. And generally, alkyl halide used as a solvent for non-polar and moderately polar compound. For example, carbon tetrachloride, carbon, or we have the chloroform or the dichloromethane. All these, or the bromoform, all these examples are of the alkyl halide, and these alkyl halides are used as a solvent. Many chloroalkanes are toxic and carcinogen. For example, I already mentioned the carbon tetrachloride is carcinogen, or hexachlorobenzene or hexachlorocyclohexane. All these are carcinogenic. Now, come to the reactions of alkyl halide. Look at the structure of the alkyl halide. This is the sp3 carbon and this is the halogen. Now imagine if any nucleophile will come, this halogen will eliminate, or this nucleophile can abstract the proton from the carbon and the elimination can occur. So we may say alkyl halides are generally undergoes nucleophilic substitution and elimination reaction. These are two very important and main reactions of alkyl halides. Beside this, look at this. When we have the alkynyl halides, aryl halides, or alkynyl halides, they have different reactivity than alkyl halides. And generally, these type of alkyl halides do not undergo SN or E reaction. Okay, I will discuss how. Now, similarly, vinylic halide and phenyl halide, they are generally unreactive in substitution reaction because they are resonance stabilized. So it is difficult to substitute the halide which is directly bonded with these type of the carbon, right? Now come to the reactions of alkyl halide. Like as I discussed in the two slides before, that alkyl halides generally undergoes two type of reaction: nucleophilic substitution reactions and elimination reactions of alkyl halide. In today's lecture, we will focus on nucleophilic substitution reaction. Now, how we can define the nucleophilic substitution reaction? What is nucleophile? We will discuss the type of the nucleophile after finishing these general mechanism. Now, you can see a nucleophile could be generally two types. It may have the negative charge, or it may have the unbonded or non-bonded lone pair of electron, or it is an electron-rich species. Now, nucleophile can attack to the nucleophilic center of the alkyl halide. By this way, this X could leave as a leaving group, and nucleophile will generate the new bond between nucleophile and the carbon. Now, in as I mentioned, in nucleophilic substitution reaction, nucleophile displaces this leaving group, and this alkyl halide is known as the substrate. Nucleophile could be a Lewis base. It could have the lone pair of electron, and it could have the neutral or the negatively charged species. Now, leaving group is species that takes a pair of electron when it departs. This is the general um, explanation of this reaction. Now, often the substrate in a nucleophilic substitution is an alkyl halide, as I discussed, because this is the alkyl group and this is the halogen. And the leaving group is the halide. Definitely, if it is alkyl halide, the leaving group should be the halide. It could have the chloro, bromo, or iodo group. Now, let's see individually the nucleophile, alkyl halide, the nucleophile and the carbon, the product and the leaving group. What is the nature of these two? As I mentioned, when nucleophile attack on this nucleophilic center, nucleophile donates the lone pair of the electron to the substrate, which results the bond between carbon and the leaving group breakage, giving both the electron to the leaving group. Ultimately, what happened? The nucleophile uses its electron pair to form a new bond or new covalent bond with the carbon substrate. And this leaving group gains the pair of electron originally bonded in the substrate. As you can see here, the alkyl halide bond cleave heterolytically. Why heterolytically? Because halogen is taking its lone pair, its total electron, and it is creating the charge on this carbon. So that's why the bond cleavage in alkyl halide is heterolytic cleavage. Now, This heterolytic cleavage result in the formation of the two type of the nucleophilic substitution reaction, which can be explained by the bond breaking and bond making process. As you know somehow that there are two types of mechanism are possible. The first type, SN2 reaction, which is basically an example of concerted mechanism, and second type is the SN1 mechanism, which is basically the stepwise mechanism. Now we will discuss that how the nucleophile bond as the leaving group leaves in SN2 reaction, and how does the leaving group leave first and then the nucleophile bonds in the SN1 reaction. Let us see in detail the SN2 and the SN1 reaction, very important reaction in the nucleophilic substitution reaction of alkyl halide. Now, in SN2 reaction, which is also known as the concerted mechanism, it is proceed via the transition step. Now, when any nucleophile attack to the nucleophilic center, by this way, it involves the transition state in which nucleophile is making the bond with the carbon and the leaving group breaking the bond with the carbon, and ultimately we have the compound. Now, this compound has some different stereochemistry. We will discuss in detail that how it happens when a negatively charged nucleophile brings an electron pair to the carbon, which is basically having the positive charge. Bromine or the bromide or the halide begins to move away with an electron pair, and O carbon bond in this case partially forming, while carbon and halogen, like in this case we have the C and bromine bond, is partially broken. And configuration of carbon begins to invert. Configuration means its stereochemistry is begin to invert. If it is a chiral molecule, this chiral molecule, we know already that we have the R or S configuration. This stereochemistry will be changed. We will discuss with some example in next slides. Now see, ultimately, OC bond formed and the halogens departed, and the configuration of the whole compound is inverted. And this configuration is only depend when we have basically a chiral molecule. Keep remember, if we do not have the chiral molecule, stereochemistry cannot be changed. Now come to the rate of the reaction, means kinetic of the reaction, that how many molecules are taking part in the rate determining step. When we are talking about the SN2 reaction, in SN2 reaction, both the nucleophile and the alkyl halide are taking part in the rate determining step. What is rate determining step? The step which occur or which consume a lot of time over all the reactions. For example, I'm writing here the rate of the substitution reaction is linearly dependent on the concentration of the nucleophile and the alkyl halide, which is the substrate. So that's why this is an example of second order reaction. Why second order reaction? Because two molecules are taking part in the rate determining step. So OR is the second order or the bimolecular reaction. Let us see the stereochemistry as I discussed of SN2 reaction. Stereochemistry means configuration. Generally, in SN2 reaction, if you have the chiral molecule, configuration is inverse. This is basically an alkyl halide. This carbon is basically a chiral carbon bonded with four different groups. We have hydrogen, methyl, bromine, and the ethyl group. So four different groups. And this is basically a molecule having R configuration. When we move the direction from the bromine, ethyl, and the methyl group, this is moving our I toward the clockwise direction. So you may say this carbon is having the R, the rectus geometry. When nucleophile attack to this carbon center, bromine will depart, and the inversion of configuration will take place, like a flipping of umbrella. Okay, now you can see and you can visualize the eyes. Now this is the hydroxy group having the priority, then ethyl and then the methyl. Now this is moving like in this way, and this molecule now having basically the S configuration. So you can see that how nucleophile attack to the carbon and its stereochemistry is changing rapidly. Now the nucleophile approaches to the substrate carbon from the backside opposite the leaving group. Means, for example, nucleophilic is actually attacking from the 180-degree where where the leaving group is. By this way, nucleophilic substitution of the leaving group results in the inversion of configuration of the substrate carbon. What is nucleophile? As I mentioned, I will discuss that the type of the nucleophile. Nucleophile, a reagent that seeks a positive center. If if any species is seeking the positive center, it means they must have, or this is the electron rich species. Typically, a nucleophile is a Lewis base having the electron pair or the neutral or the negative charge. Means there are three type of the nucleophile generally. Means it could have the electron pair, it's a neutral or the negative charge. Two types generally. Okay. Now nucleophile means nucleus loving. Phile derived from the Greek word phila means the loving. As I discussed, nucleophiles have a lone or unshared of electrons. For example, these examples are of the negative charge nucleophile, for example, hydroxide, methoxide, and the amide. All these three species having the negative charge. While in this case, when we have the water molecule or the methanol or the ammonia, they have only the lone pair. These are the neutral species, but because of these lone pair, they can act as a nucleophile. Now, this is the positive center for attacking the nucleophile. Now, example I gave here for the negatively charged nucleophile. This is the negatively charged nucleophile. When it is attacked on the nucleophilic center, this halogen will depart and will give you the product and is the leaving group. And this is an example of the neutral nucleophile. Keep remember, student, when a nucleophile which is neutral is attacking on a alkyl halide, first it will give you the positively charged product. Then it will rearrange to give you the neutral product. So you can see here when neutral nucleophile results initially a positively charged product, and a neutral product is formed only after a proton is removed from the atom with the formal positive charge. There are some nature of the leaving group as well. To be a good leaving group, the substituent must be able to leave as a relatively stable or weakly basic molecule or ion. Generally, a small molecule or a small charged species are not the good leaving group. For example, hydroxide ion is not a good leaving group. Methoxide ion is not a good leaving group. Fluoride ion is not the good leaving group because they are very small and their charge is very small. They are much strong nucleophile. That's why they are not the good leaving group. While iodine comparatively with bromine and the chlorine is the much very good leaving group. While this tosyl group or methyl group, they are also the good leaving group. Water in form of neutral and ammonia in form of neutral, they are also a good leaving group. These are all examples of the good leaving group. These are the structure of the tosylate and the methylate. Tosylate, toluene, when bonded with the sulfonate group, or methylate, methyl sulfonate group. Now we have the next type of the reaction, which is the SN1 reaction. It is also known as the stepwise mechanism because it's generally occur with the formation of the carbocation. Here you can see when alkyl halide, generally we have the 3-degree alkyl halide. It is basically proceed via the SN1 reaction. In the first step, the halogen bonds and the carbon bond will be broken to give you the carbocation and the halogen, the halide. By this way, this step is also known as the rate determining step, and this is the slowest step. And we generally can say the SN1 reaction depends on the first step only, while step 2 and step 3, which is basically the attack of the nucleophile and then the removal of the proton, they are basically very fast step. And SN1 reaction do not rely on these two steps. It is depend on the first step. This is the general example. Let us see some specific example. For example, here we have a tertiary butyl bromide. In the first step is also known as the ionization of alkyl halide. Means halogen and carbon bond will cleave to give you this stable carbocation. Now you can imagine 3-degree carbocation is much more stable carbon reactive intermediate, and we have discussed already in reactive intermediate lecture. Now by this way, this step is a slow step and the rate determining step. I will discuss the rate determining step with an analogy as well. The second step, with the fast step, the nucleophilic attack at the carbon positive center, which result in the formation of the protonated um, intermediate. Then in the last step, deprotonation will occur to give you the neutral product. As I mentioned, the rate of SN1 reaction depends only on the concentration of the alkyl halide, and it is independent of the concentration of the nucleophile. Generally, a nucleophile is the solvent in case of SN1 reaction. It's a general perception. Okay. Now, in other words, the SN1 reaction is a type of the first order reaction. That's why it is also known as the nucleophilic substitution unimolecular reaction as well. Now here I mentioned that why we call the rate determining itself. This is basically an analogy. This is the basically a sand clock. You can see here this is basically the sand, and this narrow opening rate is basically, let's see the explanation. The opening A is much smaller than opening B, and C overall rate at which sand reaches the bottom of the hourglass is limited by this rate at which the sand falls through the opening A, and hence opening A is analogous to the rate determining step of the multi-step reaction. Means opening B and opening C will do not affect uh, the rate of the opening A. That's why the all time depends on the opening A. Similarly, in SN1 reaction, the rate depends on only on the rate determining step, which is basically the first step. Okay, now SN1 reaction generally favored 3-degree alkyl halide. Why it is favored 3-degree alkyl halide? Because in 3-degree alkyl halide, 3-degree carbocation generates. And we have discussed already in case of the carbocation, this is the stability order of the carbocation. 3 is the most and the methyl is the worst stable carbocation. And the more stable the carbocation form, the faster the SN reaction will occur. Now, stereochemistry means, for example, in case of SN2 reaction, inversion of configuration takes place. What is observed in stereochemistry of SN1 reaction? Let us see. This is basically the first step in which we took basically a chiral molecule, and the first step is the departure of the leaving group, which is the halide, which provides the trigonal planar geometry and having the carbocation. Now, there are two chances. Nucleophile can attack on the left side, or nucleophile can attack on the right side by this way. I mean, attack from the left side and attack from the right side. In both cases, if it is attacking from the left side, we have the R molecule, Or if this nucleophile is attacking on the right side, we have the S molecule. So by this way, we have the equal chances of attacking the nucleophile, and we have the equal mixture of R and S. And this equal mixture is basically giving you the R and S, which is known as racemic mixture. So in SN1 reaction, generally racemic mixture formed. Solvolysis is the process which is generally occur in SN1 reaction. We never found solvolysis in SN2 reaction. What is solvolysis? When solvent basically cover the carbon positive center. Okay, when for example we have the water as a solvent, water will serve as a nucleophile as well as with the solvent, and it will make uh, the carbon positive center, and it will stabilize the carbocation by solvolysis process. Similarly, when we are using a methanol as a solvent, methanol will stabilize the carbocation by the process known as methanolysis. Many of the SN1 reactions we have seen would be called solvolytic reactions. Okay, here you can see we have a 2-bromobutane in which the water molecule is acting as a solvent as well as the nucleophile. Okay, it will basically be having as a hydrolysis process or solvolysis process. This is the example of the methanol, which is acting as a solvent as well as a nucleophile to give you these products. There are four important factors who actually affect the SN1 reaction and the SN2 reaction. What are these? The first factor is the structure of the substrate. Now, structure of the substrate is very important who can affect SN1 reaction and SN2 reaction. The second one, which is the important factor, is the concentration. Concentration of the nucleophile, concentration of the substrate. It is also can affect the SN1 reaction and as well as SN2 reaction. The third factor is the effect of the solvents. Solvents play an important role in affecting the SN1 and SN2 reaction. And the fourth factor is the nature of the living group. What type of the living group is? It is the small size, the bigger size, the neutral, or vice versa. So let us see some explanation of these factors, that how they can affect SN1 and SN2 reaction. Now, that how the structure can affect the SN2 reaction. General order of reactivity toward the SN2 reaction is uh, generally SN2 reaction proceed rapidly in methyl, then 1 degree, then 2 degree, and is rarely observed in 3 degree or vinyl or aryl. Or we can say SN2 reaction do not undergoes in 3 degree or vinyl or aryl alkyl halide, because of there are some factors that why SN2 reactions it is not possible or do not undergo in 3 degree or vinyl aryl halide. I will show you by means of the example. Here, the main reason is steric hindrance. Due to bulky substituents near the reaction site, sometimes SN2 reaction do not proceed. As you know, that SN2 reactions are basically a single step reactions. Now, you can see here, when this nucleophile attacked to this alkyl halide, this is the primary alkyl halide. Now, this nucleophilic center can attack this carbon, this nucleophile can attack this nucleophilic center very easily. There is no crowdness, there is no steric hindrance, and this reaction proceeds rapidly. Similarly, if you have a 2 degree alkyl halide or the 3 degree alkyl halide, this nucleophile attack to this nucleophilic center and it may cause a crowdness. So these steric hindrance slow down the reaction in case of the 2 degree alkyl halide. So that's why 2 degree alkyl halide proceed the SN2 reaction much slower than the 1 degree alkyl halide. Now imagine when you have basically a more bulky group, that how this bulky group basically allow this nucleophile to be attacked, and you have much more steric hindrance, okay, to proceed this reaction, and it is very slow. And imagine if you have a 3-degree alkyl halide, how much steric hindrance you have. And this steric hindrance, it is basically not allowing this nucleophile to be attacked on this nucleophilic center, and it is extremely very slow. So this is the main reason that generally SN2 reaction occurs in primary or in secondary alkyl halide, and it is never observed in 3-degree alkyl halide. Note, SN2 reactions are not possible, or they are not observed in vinylic, aromatic, or acetylylic alkyl halide, because here substitution is very difficult. They all are sp2 hybridized. Now let us see the in SN1 reaction, that how the structure can play its role. General order of reactivity toward SN1 reactions are three are more favorable than the methyl group. The reason, the carbocation. We have discussed the more stable the carbocation form, the faster the SN1 reaction can occur. Okay, now how are the factors who can stabilize the carbocation? We have discussed in our previous lecture that there are two most important factors: inductive effect and the hyperconjugation. The more substituted carbocation we have, it is more stable because of the inductive effect as well as the hyperconjugation. So allylic halides and benzylic halides also undergo the SN1 reaction because they have the resonating stabilization. Yeah, resonance stabilization. Second one, the effect of the concentration and the strength of the nucleophile. SN1 reaction, they depend on the concentration of the nucleophile. So a nucleophile does not participate in the rate determining step. So we can observe that concentration of the nucleophile do not affect the SN1 reaction. While if you have the SN2 reaction, they both depends on the nucleophile as well as the alkyl halide. So the concentration of the nucleophile may affect the SN2 reaction because it is taking part in the rate determining step. Now, identity of the nucleophile, it is measured in the term of the relative rate of its SN2 reaction with a given substrate. And you can imagine, keep remember, a negatively charged nucleophile is much stronger in nucleophilic substitution reaction as compared to the positively a neutral nucleophile. You can see here this methoxide ion is rapidly reacting as a nucleophile to give you this product, while this methanol is reacting very slow because it's a neutral nucleophile. So the nature of the nucleophile also plays an important role in nucleophilic substitution reaction. The same thing as I mentioned in the previous slide, the negative nucleophile is much better than the neutral one. For example, here you can see the hydroxide and the alkoxide ion, they are much stronger nucleophile than their neutral species. Okay, these are the third factor which affects the SN2 and SN1 reaction. Generally, SN2 reactions are favored by the polar aprotic solvent. What do you mean by polar aprotic solvent who do not produce proton on hydrolyzation? You can see here the structure of the acetone. Acetone is having the polar molecules because of the carbonyl. DMF, dimethylformamide, DMS or dimethyl sulfoxide, HMPA, hexamethyl phosphoramide, and acetonitrile. All these species are polar and aprotic because they will not affect basically the nucleophile and they will not interact with the nucleophile. Hence, polar aprotic solvent favored SN2 reactions. And similarly, in SN1 reactions, the polar protic solvent they favored because they take part in this solvolysis step as well, and they also behave as a nucleophile as well. Like for example, ethanol, methanol, or water, they behave as a solvent, and they behave as well as a nucleophile in case of the SN1 reaction. Same thing as I mentioned, that solvent plays an important role in SN1 reaction, but the reason are different from the SN2 reaction. Solvent effect in SN1 reactions are due to the largely stabilization or destabilization of the transition state. This is basically a 3-degree alkyl halide, and in this case, if you have basically a solvent, it is playing the important step, and it is basically stabilizing this transition state. The nature of the leaving group. Leaving group departs with the electron pair that was used to bond them to the substrate. The best leaving group are those that become either relatively stable anion or a neutral molecule when they depart. So, generally, the bigger and resonance stabilized group are the most stable or the good living group. Like tosylate is 60,000 much more stable living group as compared to the hydroxide amide or the alkoxide. And the worst living groups are OH negative, the NH2 negative, and the RO negative. But if they become protonate, they can be the good living group. Like hydroxide, when get protonated with the acid, become the good living group. This is the order of the living group. Okay, now here, as I mentioned, for example, OH is individually is not the good living group. As I mentioned, it's a poor living group. One get protonated, it become the good living group. Okay. Other weak bases that are the good living group in the previous slide, as I already mentioned, the paratoluene sulfonate or the tosylate group or an alkyl sulfonate group or as alkane sulfonate. These are basically the good living group because they are resonance stabilized. That's all for today's lecture.